Hello everyone, welcome to lecture 2 of week 2 of the course Simulation of Modern Power Systems. In this discussion, we will discuss the first preliminary primary technique of solving power flow analysis, which is known by the name Gauss-Seidel method. Both Gauss and Seidel, in fact Gauss was the inventor of this method or technique, and Seidel was the first publisher or person who reported this method to the research community. And that's how the attribute or the sort of credit goes to both of them, and hence the method's name is by their names, Gauss-Seidel method. The last discussion we have finished on the different types of equations which are involved in power flow analysis, and in order to solve these equations, what types of buses do we have to assume in power flow analysis so that we can ensure mathematical consistency or numeric observability in terms of equations involved, and the corresponding unknowns in terms of voltage magnitudes or phase angles, or the real and imaginary part of voltages based on whether we choose the polar version of voltage or the rectangular version of voltage. And what we have seen before I go deep into the discussion is that the equations, the power flow equations, that they are nonlinear equations, transcendental when we choose voltage in polar coordinates, and quadratic when we choose voltages in rectangular coordinates. So, it is pretty obvious that given these transcendental forms or quadratic equations, which are in terms of voltage variable products, the equations are nonlinear, and the typical KCL, KVL, nodal or mesh analysis based understanding that we have had for typical electric circuits where sources are defined in terms of voltage source or current source, the same linear analysis is now no more applicable for the nonlinear equations that we have at hand. And the reason for this non-applicability, or the primary reason of the equations becoming nonlinear, is our sources are not typical independent ideal voltage source or current source. They are power generation sources, and whenever we have power is always a product of voltage and current, and hence the corresponding equations have a nonlinear form. So, if these equations have nonlinear forms, then it is imperative that we will have to figure out or understand different forms of techniques rather than simple simultaneous linear equation based analysis or Gauss elimination based analysis. We will have to understand other forms of techniques or other techniques which can solve these equations. Because of this nonlinear form of equations, unfortunately it is not possible to find direct closed form solutions of the unknown variables. Different researchers over the years have tried doing so, but so far no I would say no acceptable closed form solution has been obtained yet. It still remains an open-ended problem that if we can have voltage magnitude and phase angle in terms of some mathematical form, let me call that form to be let us say capital F, which is having all known injections in it, and similar equation for reactive power equation which has Pi and Qi as the known terms, then there would not be any need, if this was possible, then there would not be any need to understand or do power flow at all. That has not been obtained yet, so we will see if that can be achievable at all by any mathematician or physicist or researcher. And that is the reason why power flow analysis is essential, because this is not possible, wherein we have to find the unknown voltage phasors, and these equations being nonlinear, the corresponding techniques that we have to resort to are either iterative or recursive techniques. I personally prefer using the terminologies iterative and recursive, although literature has different forms or names for these iterative or recursive techniques. In fact, in certain research papers, you would also find Gauss-Seidel method to be an iterative method. I somehow or feel that no, Gauss-Seidel method and the next technique that we would see Newton-Raphson technique, again named after Newton and Raphson, similar analogy to the way Gauss-Seidel were sort of thanked or acknowledged for their method. Newton-Raphson technique is actually an iterative technique, whereas Gauss-Seidel is a recursive technique. This is my preference, although different textbooks and different other literatures may consider both of them to be iterative or recursive. The reason for this recursion versus iteration will become evident as I explain each of these techniques in detail. These two techniques have been there for several decades now, or I would say almost more than a century now, and these are techniques which are entirely mathematical, and they can be used to solve any nonlinear equation. For our case, we are considering those nonlinear equations to be power flow equations. It is not necessary that Newton-Raphson and Gauss-Seidel method are only meant to solve power flow equations. They can be used to solve any other nonlinear mathematical equation. The third technique, which we will also discuss as part of this course, is decoupled or fast decoupled method, which is an extension of Newton-Raphson method. This technique, on the other hand, is a purely, I would say, it is a purely power engineering based technique. It is not a generic mathematical technique which can be used to solve any mathematical nonlinear equation. No. Fast decoupled or decoupled method, it was curated or created or thought over a long period of time, and the power engineering research community took time to understand and appreciate this method. It is a technique which is specifically tailored to solve power flow equations and not all mathematical equations. In fact, I would also state the importance of this method. This technique is the industry grade technique. It is the industry grade technique which is used to solve actual power flow for real life power networks. All industry grade solvers, they are based on decoupled or fast decoupled methods. They are not based on Gauss-Seidel or Newton-Raphson method. There are reasons for that. Please have patience. It would become evident or clear when I explain the techniques in detail. The last technique, that is holomorphic embedded method. It was invented by a physicist named Antonio Traes, not very late, somewhere in early 2000 or late 2000. Antonio Traes, a physicist, reported or filed a patent where he mentioned that holomorphic embedded method, which draws its inspiration from Gauss-Seidel method, is a further advanced technique which can be used to solve power flow equations. It is not as matured as compared to fast decoupled Newton or Gauss-Seidel. There are problems or issues in holomorphic embedded method, and the research community is actively working on it even in current times on overcoming the challenges that are there in the holomorphic embedded method. And that's the reason why I'll not be discussing this technique at all as part of this course or discussion. We'll focus on Gauss-Seidel, Newton-Raphson and decoupled or fast decoupled techniques. So what does Gauss-Seidel method do? It doesn't directly solve the power flow equations, alpha and beta numbered equations that we saw in the previous slides. What it does is, it rewrites or reorients the power flow equation in a certain form, and then the method is applied to sort of find the corresponding voltage magnitude or voltage phasors. So irrespective of whether the complex power flow equation has voltage as polar coordinate or a rectangular coordinate, it doesn't, Gauss-Seidel method doesn't exclusively find the voltage magnitude or phase angle, or it doesn't exclusively find the real and imaginary part of voltage. What it actually finds is the voltage phasor directly, which is, I would say, VI, which is VI magnitude and phase angle, or EI plus JFI, where J is root over of -1. The power flow equations that we have seen earlier, they are based on these variables. What I am trying to say is Gauss-Seidel method, instead of finding these, it directly gives you this value, and hence there is no necessity of assuming the voltage coordinates to be in polar or rectangular version. It is required, but not exclusively. We will see that where it is required. And that is the reason why in literature you will not find Gauss-Seidel method being explained in polar version of coordinate or rectangular version of coordinate. So let's see how the Gauss-Seidel method works. We assume a power network having n buses, and these n buses have been numbered from bus number 1, 2, 3 and n. There is absolutely no necessity or no assumption or ordering required in defining these numbers. These can be arbitrary numbers. I have just chosen these natural numbers to be a convenient way of representing or numbering these buses. The numbering as such is not that important. These numbers could be labeled as alpha, beta, gamma, A, B, C, D, A1, A2, A3 and so on. It's not necessary, but it is important to know what bus is slack bus, PQ bus or PV bus. That information should be known. And again, for the sake of discussion analysis, the way I have worked over the years, I generally prefer assuming for a given n bus network, I assume that bus 1 is my slack bus. Even if the data sheet mentions that bus 1 is not a slack bus, definitely for power flow, the data sheet of the power network would have one of those buses as slack bus. I rechange or reorder the bus number so that bus 1 for me remains the slack bus. The other bus can replace the number of actual slack bus which it was originally given in the data sheet. With this, if my bus 1 is slack bus, that means its voltage phasor is already known. So its voltage magnitude is already known. This is becoming known from active power loss minimization exercise that we briefly discussed or touched upon in the previous discussions, and the corresponding phase angle is also known. For the sake of convenience, I choose this phase angle to be either 0 degrees or 0 radian, although you can still use Gauss-Seidel method by choosing the phase angle to be plus minus x degree or x radian. X can be any real number. The solution or the overall losses, injections, they will not change. What will change are only the voltage phase angles of remaining other buses. So we have already seen this complex power injection equation thanks to VI conjugate and II product. So if SI conjugate is VI conjugate II, where PI and QI are the respective real and reactive power equations at bus number I, and J being the complex operator which is root over of -1. I can expand or rewrite the current injection at bus I in terms of bus admittance matrix elements and the remaining known unknown voltage phasors starting from bus 1 voltage, bus 2 voltage all the way till nth bus voltage phasor. And in this form, what I can now do is, in order to obtain this mathematical form, Gauss-Seidel method works under certain conditions of mathematical orientations. Essentially, it is all to do with the initial choice of voltage phases that we choose, because essentially these are nonlinear equations. Any iterative or recursive technique would require a good initial choice so that the final solution can be easily obtained, as direct closed form solutions of voltage and phase angles are not possible till date. So in order to Gauss-Seidel method to be applicable, the mathematical rewriting of the actual given equation has to be of a particular order, specifically from the divergence or convergence perspective. So for Gauss-Seidel method, typically power flow engineers or power engineers for power flow analysis, they prefer writing this complex equation into this form. Now how does this equation come in? The voltage I conjugate of ith bus, it is divided on this side because division is possible. Why? Because voltage is a potential difference. If the voltage is 0, that means it is the ground bus or the reference bus or the zero potential bus. In power flow analysis, earth or zero potential bus never ever physically occurs. So voltage is definitely not zero, and hence this division is possible. We bring this voltage I conjugate down on the denominator form and rewrite all other voltages with their corresponding Y bus elements into the left hand side with a negative time, so that we are left only with YII and VI on the RHS part. Now, YII is also a physical self-impedance or admittance of bus I. It's a physical power network. It's not just a single bus which is floating free with respect to ground. Even if it was to be floating, then its voltage cannot be obtained, and hence power flow analysis cannot be done. So, since YII is a self-admittance, that is also not zero, and hence YII can come to denominator. And now, with this as my closed form voltage form, where Pi and Qi are mostly known for PQ buses, we will find a way also of knowing Pi and Q for PV bus also. We are getting a unknown Vi in terms of remaining other unknowns here. So, that is where the Gauss-Seidel now method becomes applicable. So, let us see how do we do. As I mentioned, we start with a flat start of, we choose an initial choice of voltages because these are nonlinear equations. Preferably, we choose them to be the flat start voltage, where our voltage magnitude for PQ buses would be typically close to 1 per unit. So, we choose them to be 1 per unit for voltage magnitude. Since we have chosen angle reference of slack bus to be 0, so it is also convenient to choose initial choice of other bus voltages to be also 0. And for PV buses, the voltage magnitudes are fixed and specified as per active power loss minimization exercise. These may be equal to 1 per unit or need not be equal to 1 per unit. Often students interpret or assume that PV bus voltage magnitude is always 1 per unit. No, it is not a necessity. It all depends on at what voltage profile the system active power loss can be minimum possible, and hence the voltage magnitude of PV bus or slack bus or angle reference bus need not be 1 per unit always. With this initial choice and this form of voltage, since in our case Vi or V1 is known, why? Because bus 1 is slack bus, we would now start to understand what would be the voltage form for bus 2. So, if I take I as 2, then I have V2 equal to 1 by Y22, P2 minus JQ2, assuming bus 2 to be a PQ bus. So, P and Q for bus 2 are known, divided by V2 conjugate minus Y21 V1 minus Y23 V3 and so on till I have Y2n Vn phasor. For all voltage phasors like V2, V3, Vn, I already know what is my initial choice. So, I plug in those values in the initial choice forms over here. V1 is anyway known. I eventually get a RHS form which is completely known in terms of these initial choices. And this, as per the KVL or reoriented S form, should be equal to V2. So, I now get a new value of voltage at bus 2, and this exercise continues for bus 3, bus 4 all the way till bus n. So, for initial choice of voltages which are represented by the recursion number 0, I have till now got V2 0, V3 0, V4 0 and Vn 0. Once I know these V zeros in terms of initial choices, the entire RHS becomes a known quantity, and this has to be equal to V2 1 as per the complex equation analysis that we saw. So, recursion number gets updated, I get a new value of V2 which need not be equal, or which definitely is not equal to V2 0. Now, when I go for bus 3 voltage update, I have already got the latest value of voltage for bus 2. So, I will reuse that same value as it is. For all other higher numbered buses like V4, V5, Vn, I don't have the updated recursion number, so I keep them as 0th choice as it is. And using all this, now I get V3 1. When I find V4, I already know the latest values of V2 and V3, so I use them as it is, as I have obtained. And for all other higher number buses, I retain the 0th index. And this is how the exercise repeats till I reach the Vn voltage update, Vn1. Obviously, when I try to find Vn1, all other voltages on the RHS would have the higher subscript 1 because n-1, n-2 and all of the lower number buses have received their latest value except for bus number 1, which is still the slack bus or angle reference bus. So that's how Gauss-Seidel method finds new voltages, and the reason why these are called as recursions is because of the fact that when I try to find the update voltage of ith bus for all buses numbered from 1 to I-1, I will use their latest recursion update, whereas for buses numbered from I+1 to n, I will still use the previous recursion number, and that is where the concept of recursion comes in. In a recursive technique, whatever is my latest solution value, I work entirely on that. Usually in iterative techniques, if I have n unknowns, all these n unknowns will get updated in a single go. In recursive technique, if I have n unknowns, then at every stage of recursion, each of these voltage variables can have their individual updates. In iterative techniques, the unknowns form a single group and then this group gets an update in a single go. That is where the difference of recursion or iteration comes in. In Gauss-Seidel method, since this recursive form of voltage updates are being used, that is where the Gauss-Seidel method is called as a recursive technique. In order to accelerate the method, the factor of acceleration factor alpha, which is typically between 1.4 to 1.6, can also be used, where Vik is the same value that was obtained that is obtained using Gauss-Seidel method, and the accelerated value, they are based on the previous update values or the latest update values. Now, as I mentioned, the applicability of Gauss-Seidel is true in this equation as long as P and Q are known. P and Q are definitely known for PQ bus, so Gauss-Seidel application for PQ bus is not a problem. However, for a PV bus, Q is not known a priori. What rather is known is the voltage value. So if PV bus Q is not known, then is there a way to apply Gauss-Seidel for PV buses? Yes. If Q is not known a priori for PV buses, we already know the Q expression in terms of polar or rectangular coordinates of voltages. Let us use that equation and evaluate the Q value of PV bus, ith PV bus at the known voltage values, which is the expression shown over here. Now, in order for this ith bus to remain a PV bus, using this injection and depending on the demand which is converted on the PV bus, we find the corresponding generation. For this ith bus to remain PV bus, this should be between a typical lower limit or upper limit as defined by the corresponding field excitation control of synchronous generator. So, if QGI is within limits which has been obtained from this discussion here, then the corresponding voltage magnitude should not change. Now, since we know what is the injection of PV bus using this expression, can't we apply Gauss-Seidel method as it is? Yes, we can do so. So, we use the calculated value of injection as obtained here and plug that value into the Q value wherever it is to be required in the Gauss-Seidel update equation. We solve this equation in similar form as we did for other PQ buses equations in Gauss-Seidel, and we are able to find this voltage. Now, this voltage is not just a number, it is a complex number, it is a voltage phasor, in which if QGI is within limits, then essentially this condition should be true over here also. In order to ensure that the voltage magnitude does not change for PV bus, it is not necessary that the corresponding VIK mod refers to this fixed voltage magnitude. It could be a different number. So, for PV buses, we have to involve this voltage magnitude correction exercise, which is as explained here or as shown over here. Whatever is the VIK value that we are getting, we figure out its magnitude. So, we divide this V with its corresponding magnitude. It is essentially left over with 1 at an angle theta at the kth recursion, and we are multiplying this phase angle theta ik. The phase angle can change for a PV bus. We are multiplying this phase angle with the voltage value which is specified for this PV bus, and that is how voltage correction gets done. The phase angle remains free, the voltage magnitude however remains frozen. So, this is the case only when QG is within its limit. What if the case the QG is not within its limits? If it is not within its limit, that means excitation control is all lost. Generation cannot be beyond its lower limit or upper limit as defined by the capability curve or excitation control of the corresponding generator. So, how do we find the corresponding value? We find the corresponding Q first, then use demand equation to find the corresponding generation value. Compare it with QG min or QG max. If QGI K is trying to be lesser than QGI lower bar, then physically it is not allowed. The control or practical operation can be that QGIK can worst case be equal to QG lower bar. Similarly, if QGI at the kth recursion is trying to overgo the upper limit, this is not practically allowed. In that case, QGI has to be frozen or set at QGI upper bar. If QGI becomes frozen depending on the violated limit, demand is known. Indirectly, we are now freezing QI injection for every such PV bus, essentially meaning that PV bus now has to become a PQ bus. So, when the violation happens, we find the corresponding Q limit and use this Q value which has been frozen or fixed depending on which Q limit is being violated, and use that to find the corresponding voltage update. Since the PV bus is now a PQ bus, voltage magnitude is now free. So, no voltage correction is required for this converted PV to PQ bus. It may happen in Gauss-Seidel that a PV bus which was actually PV in initial iterations or recursions has converted to a PQ bus. We should always look for a possibility that whether this PQ bus can go back to PV bus or not. So, that check is explained here. For converted PV to PQ bus, we have to first ensure that if it becomes or goes back to PV bus, its voltage magnitude should go back to its actual specified value. So, we do the voltage correction first, use this voltage phasor to find the latest injection, then use it to find corresponding generation. If generation at the kth recursion is within its limit, this converted PQ bus goes back to PV status with voltage specified or magnitude going back to VI specified. If QG is not within its limit, then there is no need of voltage correction. The bus remains as PQ bus, and we can use the method explained in the previous slide to find the corresponding voltage value. If it goes back to PV bus, voltage becomes frozen and the only phase angle part or variable is the unknown. So, we use slide number 10 to find its corresponding voltage phase angle. All this goes on till a convergence or a closure is reached. We call this convergence to be reached when the difference between the calculated injection value and specified injections, their differences goes down to 0. Ideally speaking, it should be perfectly 0, but since these are mathematical techniques, we often use a mathematical tolerance to have a trade-off between the number of recursions involved and the time involved and the effort involved in finding those voltage solutions. Basically, the trade-off between time and accuracy. If we will set this tolerance to be perfectly 0, it may happen Gauss-Seidel may take infinite recursions to find the same voltage solution which you would have obtained probably with little less accuracy when the tolerance is not close to 0. So, as long as And this infinity norm here essentially is referring to the maximum absolute value of vector x, where all these voltage, injection differences are true for all buses 2 to n. We find the corresponding calculated values as per the expressions given over here, and the same convergence check or tolerance check can be made on voltages also, because in every recursion the voltages are also getting updated. The next slide will talk about a bit on the convergence of Gauss-Seidel method, how good or bad the convergence behavior of Gauss-Seidel method is. We have understood that this complex equation gets rewritten into a particular form where Gauss-Seidel works well for this form of voltage updates. So what we would do is, let us choose x to be our unknown voltage phasor, and I define this equation as g of x equal to 0, where x is the unknown and g is the entire mathematical form of pi minus jqi minus this entire term sitting on the RHS of this given equation. I take it to the LHS part with a negative sign and call that equation to be g of x equal to 0, wherein with Gauss-Seidel this g of x actually it becomes x is equal to r of x divided by x minus t of x, where r of x is pi minus jqi divided by yii. Why have I mentioned x here? Because my injections, they are known quantities, probably in form of the voltages themselves, and x is nothing but the voltage phasor itself, and t of x is all other terms with the negative signs divided by yik, which is this form here. So let us see that if g of x is to be solved to find x, which is where g of x is getting transformed into this form, what we would do is we would first apply Taylor series analysis to g of x, Taylor series to g of x. If you have to find the Taylor series of g of x at some recursion update xk, then what it will give? It will give g of xk plus first derivative of g at x is equal to xk. So I will write it as g prime xk multiplied by x minus xk plus other double derivative, triple derivative and other higher order terms, which for my understanding or explanation I will ignore them. So if this is the Taylor series form of g of x at x is equal to xk, let me now substitute what is g of xk. G of xk can also be rewritten in this form with x as representing xk. So I will have xk minus r xk divided by xk plus t of xk. Furthermore, before I come back here, I will come a bit over here. The Gauss-Seidel update equation essentially indicates that xk plus 1 is r xk divided by xk minus t of xk. That is how for every other kth recursion update I am getting the next recursion update. So this is coming from the Gauss-Seidel method itself. Now coming back to the Taylor series form, so if I have to further expand this, then g prime xk would be 1 minus r prime xk divided by xk plus r xk divided by xk square minus of t xk. It goes on the right hand side and it becomes plus t prime xk almost equal to 0, because I have neglected the higher order terms here. Now, let me rewrite this also as, I'll take this x minus xk inside. What I have here is x minus xk, which is the term of these two products, plus xk minus r xk, xk plus t of xk minus x minus xk r prime xk, x divided by xk minus r xk, xk square minus t prime xk is almost 0. So, xk gets cancelled, and if I closely match this with respect to this, then essentially it is nothing but xk plus 1, and if I write this as x minus xk plus 1 is equal to x minus xk, I am taking this entire term to the right hand side, then I will have, let me define this as some function of xk, let me define the term wxk. So, I have x minus xk, which is also called as the error e in the kth recursion, and if this is error e at kth recursion, this term becomes the error at the kth recursion. It indicates from this discussion that error at kth plus 1 recursion of Gauss-Seidel is proportional to the error in the previous recursion, which means whatever error was present in trying to find x for which g of x is 0, the same error gets propagated in the next recursion also. And hence, Gauss-Seidel method is always called to have a linear convergence, which is what makes it also slower. And that is the reason why this term is, or this statement is true. It is recursive, but it has slow and linear convergence, and often Gauss-Seidel method has difficulty in finding power flow solution for heavily loaded networks where the load is pretty high. We will discuss about this pretty high load impact on voltage in terms of voltage stability problem. It also creates difficulties for networks, specifically distribution networks, where R by X ratio is very high. With low voltages, the value of X, the inductive value goes down, and hence for the same conductor to be used in transmission network or distribution network, the R remains the same, and that is the reason why low voltage networks have high R by X ratio. If they have high R by X ratio, the corresponding Y bus has dominant G, the real part, and lesser imaginary part, which creates a problem in convergence of Gauss-Seidel. It is also true for Newton-Raphson method, but then over time there have been dedicated techniques for distribution network, which we will see as part of this module or discussion. When the network is highly radial or sparse, the Y bus is also becoming sparse, which creates problem in the value of YII. If YII becomes close to 0, convergence of this equation is a problem. And in case the system is heavily compensated, specifically through reactors, if the overall line reactance becomes negative, then also Gauss-Seidel method has convergence issues. So, that is the reason or pitfall or lacuna or challenge involved in Gauss-Seidel method. Its understanding is very good, but its application for real world practical network is difficult. We will discuss through this further in our next discussion through a numeric example, which would be followed by the detailed discussion on Newton-Raphson method with voltages being represented as polar coordinates in power flow equations. With that, I conclude this discussion. I look forward to more discussion on similar lines, specifically Newton-Raphson power flow technique and the corresponding polar coordinate version. Thank you.